In a modern distributed architecture, thousands of microservices process millions of requests every second in a continuous, invisible flow, until, suddenly, they don't. When the pagers go off, the first instinct is to check the hardware. You pull up the dashboards and see CPU utilization at barely 15%, alongside plenty of free memory. The hardware is completely healthy, yet the system is entirely unresponsive. In these environments, capacity revolves around concurrency limits, the maximum number of requests a system can hold open at any single moment. Diagnosing these hidden choke points requires looking beyond processors and disks. Effective troubleshooting starts from the outside, observing how the system interacts with its users. Google's site reliability engineering teams formalized this shift with the 4 golden signals. These are the metrics that accurately reflect user experience: traffic, latency, errors, and saturation. By tracking these 4 specific, user-centric signals, engineers map the mathematical boundaries of their architecture. They see exactly where the system will bend and where it will eventually break. To understand these boundaries, we use Little's law. The average items in a system, L, equals the arrival rate, lambda, multiplied by wait time, W. Lambda represents our first golden signal, traffic. Wait time, W, translates directly to our second signal, latency. Concurrency, L, is simply the product of those two numbers. If 1,000 requests arrive per second and each takes half a second to process, the system must hold 500 concurrent requests open. This concurrency number defines our third signal, saturation. It tells us exactly how full the service is at any given moment. Traditional web servers operate on a thread per request model. For the entire wait time, a vertical operating system thread slot is locked open. But schedulers hit a hard ceiling, typically between 10 and 15,000 concurrent threads, before performance degrades. If a downstream database query slows down, latency expands. Even if the arrival traffic remains perfectly flat, the expanding wait time forces the concurrency level to skyrocket until it hits that operating system limit. Once the thread pool is saturated, any new incoming traffic is instantly dropped, generating our final golden signal, errors. The CPU sits idle the entire time. The system dies because the operating system simply runs out of space to wait for slow network responses. Tracking that wait time accurately is difficult, primarily because most monitoring defaults to reporting the average or the median latency. The median sits at 100 milliseconds, obscuring a long tail of requests stretching past 5 seconds. To measure true capacity, we look at P99, the slowest 1%. A 5-second request holds a thread open 50 times longer, consuming massive concurrency. These invisible outliers quietly stack up in the background, aggressively pushing the system closer to full saturation without moving the average latency metric at all. When tail latency exceeds timeout thresholds, the client assumes failure and retries. This instantly multiplies the arrival rate. A single outlier acts as catalyst, triggering a massive traffic spike that crashes the entire architecture. Decoupling a system's concurrency from these rigid operating system limits requires structural changes to the code itself. The first approach is replacing synchronous lotls with asynchronous I/O callbacks. Instead of locking a thread while waiting for a response, an event loop registers a callback and instantly frees the thread to process other work. Alternatively, languages like Go or libraries like Quasar for Java introduce lightweight, runtime-scheduled threads. Because these lightweight threads are managed by the language runtime rather than the operating system, the concurrency limit jumps from tens of thousands to potentially millions. Yet, even a million threads cannot save an architecture if a critical downstream database locks up completely. Eventually, any finite pool will drain. The ultimate defense mechanism against cascading failure is the circuit breaker pattern. It continuously monitors downstream error rates. When a specific service starts failing or stalling, the breaker trips, physically cutting off traffic to that specific route. By severing the connection, the system enforces a strict cap on maximum latency. It immediately returns an error rather than holding a thread open in an endless wait state. Failing fast stops the client from initiating a doomed cycle of retries, eliminating the cascading traffic spike before it begins. Robust architectures anticipate failure. They actively sever slow dependencies to protect their own concurrency pool and contain the blast radius to a single component. Architectural safeguards are blind without the instrumentation required to trigger them. White box metrics like CPU and memory usage provide a look at the engine, but they often fail to signal when the network layer is starting to choke. Site reliability engineers must instrument the 4 golden signals to detect these mathematical boundaries being breached in real time. This PROMQL code queries the true P99 latency. It isolates the exact wait time experienced by the slowest 1% of requests over a 5-minute rolling window. Alerts are built strictly on these upper percentiles. We explicitly ignore the mean, ensuring that the pager only rings when users are experiencing dangerous delays. Next, we instrument the system's explicit failure rate. This query divides the number of HTTP 500 errors by the total number of requests. Tracking this ratio, rather than raw error counts, accurately measures the true scope of the failure, regardless of the current traffic volume. Finally, we measure saturation. Saturation cannot be a generic metric. It must be tracked at the exact known bottleneck points for that specific service, like the utilization of a database connection pool or the capacity of the operating system thread limit. These precise queries combine into a unified dashboard, painting an exact mathematical picture of the system's current capacity and flow. When a massive traffic spike hits and a downstream service stalls, the P99 alert fires instantly. The circuit breaker trips, returns a fast error, and cleanly reroutes the flow of data. Downstream failures are a mathematical certainty at scale. By understanding the physics of capacity and instrumenting the right signals, engineers ensure their systems degrade predictably rather than collapsing entirely.